This video presents a quick overview of our paper. Humans intuitively watch and understand digital 3D scenes by reasonably selecting views. Users are supposed to adjust the camera by themselves, which is time-consuming. View selection for 3D objects was addressed through several approaches. In view selection at the scene level, several methods were proposed for an optimal view of 3D scenes. For example, a recent work applied the rules of residential photography. Nevertheless, existing literature has the following drawbacks. First, existing view generation methods mainly focus on objects instead of 3D scenes. Compared with individual objects, camera routines in 3D scenes are more complex. Second, though a few methods yield views for 3D scenes, they propose views according to 3D scene boundaries, that is, walls in residential scenes. For complex floor plans, the existing method yields unexpected results. Third, residential photography is not fully utilized. A digital 3D scene can be applied with photography rules, but the rules should be computational. The input to our method is a digital 3D residential scene. Our method outputs a set of views, that is, how the camera watches the scene. There are three contributions to our method. First, our method generates views for 3D scenes, especially residential ones. Second, our method is object-oriented and independent of room shapes like walls. Third, our method comprises computational interior photography. Our method comprises three steps. Firstly, objects clustering groups objects according to their functions and distances. This step yields a set of object groups. Each group expresses a batch of objects that can be photographed simultaneously. Secondly, our method proposes views according to the object groups. This step utilizes the one-point perspective, OPP, and two-point perspective, TPP, in residential photography. The OPP and TPP suggest how a camera observes a room. This step yields a set of raw views, which are not thoroughly evaluated. Thirdly, our method evaluates the raw views. This paper introduces four criteria, including room information, visibility, composition balance, and line dynamics. These steps filter the views and generate the qualified results. We first divide indoor objects into groups suitable for observation in the same view. An agglomerative clustering algorithm is adopted to build a hierarchical organization of objects, while we redefine the distance between classes. The distance between two objects is the sum of spatial and categorical distance. We utilize the 3D front dataset to obtain the categorical distance. Some results of the agglomerative clustering algorithm are presented. The top images show the top-down view of the room, and the bottom images are the respective results of their object grouping. The objects in the same group are in the same color, while the white polygons show the shapes of walls. More details are shown in section 3 of the paper. This step proposes the initial views. A view's parameters contain a camera position, which is a 3D translation, a camera direction, which is a 3D normalized vector indicating directions, a field of view, and an aspect ratio. Proposing a view is equivalent to elaborating the four parameters. The one-point perspective rule is used for each group clustered to decide the camera position and direction. The two-point perspective rule is also used. FOV decides the observation scope of a view. The distance between the camera position and the target group generally determines FOV. When the target is close, the FOV has to be increased to perceive things more thoroughly, and vice versa. The aspect ratio is usually a design decision in interior photography. Our method supports 16:9 and 4:3. More details are discussed in section 4 of the paper. Room information measures how many objects a view can see and how complete each object is. The equation mainly measures how an object part is sufficiently large after being projected on the image. Distance and volume can be considered weights. Visibility measures the sense of room depth for the audience. This measurement will be low if the camera faces the wall directly and closely. The equation calculates the furthest distance from the camera to its directions on the thing. Integration of image width and height. Composition balance measures how objects deviate from the view center. A view with objects evenly distributed on both sides makes the user's perception more coordinated according to the law of symmetry in Gestalt psychology. The equation counts the number of objects distributed horizontally according to their volumes and distances to the camera. Line dynamics are one of the most significant mechanisms for creating a sense of space in views. The impact of a view is enhanced when its borders are broken at oblique angles by sufficient lines, which refer to the object's outer contours, as shown in the figure. An interior design company of whole house customization provides the dataset. Our method is also applicable to 3D Front, which is one of the latest and most fundamental datasets for scene synthesis. We next show more results of our method. To evaluate our method, we compare it with the latest view generation method for 3D scenes and professional human photographers. Two groups of participants are invited. The professional group consists of professional photographers. The third-party group comprises university students knowledgeable in arts, photography, and interior design. Participants compared 3 images and rated them based on aesthetics, informativeness, and overall sense. 5 photographers are invited to the professional group. Each photographer was assigned more than 500 questions, and we achieved 2,933 scores for each image. For the third-party group, 31 knowledgeable participants are invited. Each one was assigned 45 questions, and we achieved 1,395 scores. Both groups indicate that though the photos taken by professional human photographers are better than ours, our method performs better than the latest research on 3D scene photography and is competitive with photographers. Please refer to our paper for more results and ablations. This is the end of our video. Thank you for watching.